Okay, welcome to the third class meeting. Today we are going to review some important definitions appearing in this paper. The first one is the notion of second-order random process. And this is very confusing. The first, mostly commonly used definition of second-order random process is that a random process x of t has ensemble average power always finite. You can extend this definition for any discrete time random process. And there are many other terminologies, but basically, I'm going to use this definition. So, here in definition 2, a second order blah blah random process means that what? The random process has always of finite power for any t. So this kind of makes everything simple. If you don't know what does this mean, then consider a random variable x and consider the first two non-central moments. Let me ask you, what is the definition of the expectation ensemble average of a random variable x? What is it? It's defined as a kind of center of gravity of this best function. The problem is that this mean is not guaranteed to exist. There are some random variables that does not have well-defined mean, even though it may have well-defined the probability density function that is exactly symmetrical with respect to 0. Why this is so? Because this integration, whether it is defined as a Riemann integral or a Lebesgue integral, may not converge for some density functions. Got it? And what is the central moment? Second order, non-central moment. It can be similarly defined as this one. And again, even if the first order moment may exist for a density function, this is also not guaranteed to exist. Whenever we have some of these random variables that does not have well-defined mean, well-defined second order non-central moment, we have huge difficulty in handling. Why? Because we even cannot resort to central limit theorem. Because our central limit theorem, widely used, requires what? Requires mean value existing and the variance existing. The variance of a random variable is defined what? It is defined as if I use the CDF and Stieltjes integral, like this. And this requires the existence of the mean, right? Got it? And also, even though the mean exists and second order non-central moment does not exist, we may still apply law of large numbers. Probably you remember strong law of large numbers applicable to random variables without variance. However, as I told you, some random variables does not have well-defined mean. In that case, you even cannot apply the strong law of large numbers. So you may say that, hey, professor, that is a very special minor cases we can ignore. Actually, it is not. Okay. People have defined random variables that does not have well-defined central moment or second order central moment, which is variance, or second order non-central moment. Even the random variables that does not have mean well-defined, but they wanted to classify these random variables because they turned out to be very, very useful in handling, for example, some stock market related predictions. So-called heavy-tailed distributions often does not have well-defined mean or variance. In that case, they classify by introducing some parameter that describes how fast the tail decays, and they call these random variables as Levy-stable random variables with parameter alpha equals, for example, 1 or 2 or something like that. Got it? So be careful. Which means when we handle random processes in this paper, we are living in a good world, like Gaussian random processes world or something similar. So here goes the set of all random processes, continuous time. And you may say that this tiny set exaggerated is the set of all second order random processes. But I still say that some non-second order random processes are very important in other applications. Got it? Usually, these non-second order random processes are very useful when our signal is far from Gaussian. Sometimes some interference may not be well modeled as a second order random process. So be careful. In this paper, the cyclostationary random process, among every cyclostationary random processes, we are only considering second order cyclostationary random processes. So it has limitation. So now probably you have noticed that this paper has a lot of restrictions or limitations. Actually, most of the papers have a lot of limitations and restrictions. They introduce a lot of under certain conditions, which means that we have a lot of constraints. So none of the papers are general theory. They are kind of handling a small subset. Why? Because within that small subset of, in this case, random processes, we have something common. It's like, suppose you have a set of, you have the set of all linear systems, and you have a very tiny subset called the subset of linear time invariant systems. Within this subset, you may use Fourier series and transform to fully characterize the frequency domain characteristic of the impulse response. Otherwise, you need some other tools. Got it? So anyway, so here goes the first important limitation of this paper, second order random process. Now, next one is proper complex. This is not well known. However, if you have taken my course in graduate level random variables and processes, I emphasize that too much actually. So you will be already sick of it, but let me repeat because some of you have no idea about that random variable. Just a second. How can I have, yeah. Sorry about the mixed order of these things, but anyway. So first, let me define a proper complex random variable first. What is a proper complex random variable? It is a random variable that has some interesting property. First, it is a random variable that generates the outcome in complex set. So suppose you have a random variable z, then you have actually two random variables jointly distributed. X is real, y is real, two jointly distributed or jointly random real random variables, which means that you have well-defined joint CDF. And if you are very fortunate, you have well-defined joint density. Ready? Now, what is the properties then? Proper means that first, you define the mean of this random variable, and it's not that difficult because it's simply the mean of real part plus j times the mean of the imaginary part. Now, you define the variance of this complex random variable in a very similar way to what you have defined the variance of a real random variable. But here, since z is complex valued, we have absolute value squared of modulus squared, and we have expectation. And we have another variance called the pseudo variance or complementary variance, defined as expectation of z minus its mean just squared. If z is real, these two expectations are the same, but if z is complex valued, they are in general different. So here goes the properties. If this pseudo variance equals 0, then z is a proper complex random variable. If not, then z is called improper. So it's an improper complex random variable. Now we extend this one to a random process. So here goes here goes the mean path of a complex valued random process. And here goes the autocorrelation function. Just autocorrelation function of a random process, right? And here goes another autocorrelation called complementary autocorrelation or pseudo autocorrelation. Here, pseudo means this is called complementary or pseudo variance. Similarly, this is called complementary autocorrelation function of z of t or pseudo autocorrelation function of z of t that does not have conjugation. And if this one equals 0 for all pairs of T1 and T2. T1 and T2 can be the same, okay? Then Z of T is proper. Just a second. Yeah. So here, the second order proper complex random process actually means that we want to have well-defined autocorrelation function and pseudo autocorrelation function. And pseudo autocorrelation function is always 0. So these two words, composite words, second order and proper complex, talks a lot about our random process. Anyway, so we are assuming that the n of t that corrupts our received signal is a second order proper complex random process. And one more thing is that we have Y-sense cyclostationarity of this second order random process. But in order to limit our interest further, here we assume zero mean Y-sense cyclostationarity. And one of the reasons is that in communications, we usually have no direct delta function in the power spectral density because it wastes a lot of power in communication. So that translates to the complex baseband zero mean complex valued random process. So it's not that limiting assumption, the restricting assumption. But anyway, so here goes Y-sense cyclostationarity. And what is it? Y-sense cyclostationarity can be defined for real valued random process and also can be defined for complex valued random process. But let me first define for real valued first. A real valued, of course, second order random process x of t is wide sense cyclostationary if first its mean process is periodic. Then we need to talk about its period. But we are not saying that cyclostationary with period t. We say cycle period t. Of course, we choose a positive number for all t. Second one is that our autocorrelation function has some strange property, like this. Ready? Actually, if you combine this first and second one, actually, the second one can be replaced as the property of the autocovariance function after you subtracting the mean process. But anyway, sometimes the second prime property, if we don't have the first property, but we have second property, is called wide sense covariance cyclostationary. Got it? So as you see, the second property is quite interesting. And let's view in the two-dimensional plane where the horizontal axis represents T1 and vertical represents T2. And let's say we have some lines equally spaced by capital T. And let's see what happens. What's the meaning of this second property? So consider some pair of sampling points T1 and T2. Let's say this one. Now, what does this second property mean? It's like this. Consider you have offset capital T from this T1, T2 pair, which means that one. So here, this is T1, comma T2, for example. Then this point is here. It's shifted by capital T to the horizontally and capital T vertically. And what does that mean? Here, you have xt1, a random variable, and xt2, another random variable. They have correlation. And this correlation is same as what? xt1 plus capital T and xt2 plus capital T. And this holds for all T1 and T2 in R square, which means that not only these two, but also this one, that one, countably infinite pair of two sampling instants have the same autocorrelation, same correlation value. And similarly, you can consider some point here. Then you shift by T horizontally and vertically, and you will find these points have the same autocorrelation value. Now suppose we focus on a single tile on this square and consider the level set of this autocorrelation function. And just for simplicity, the level sets have shown some lines like this. Got it? Then this tile will be exactly copied and pasted here, and here, and countably infinite, and there, and countably infinite. What does that mean? You have the same level sets. It's kind of you have a stamp and just stamp in this direction. And suppose here you have some other contour like that. Then you will have this appearing again and again, right? Got it? So you have this off diagonal tiles having the same level set. Since we are assuming real valued, multiplication product of two real values are commutative. So we may believe that this tile have some symmetry with these tiles. Ready? And so this is exact the mirror image of this tile, that tile. That's why I draw this diagonal tiles symmetrical with respect to diagonal line. And you may have some other contours like that, blah, blah, blah. Ready? So if you draw the level sets of this Ysen cyclostationary random processes autocorrelation function, you have this typical pattern. And interestingly, you've seen something similar to this one in linear algebra. What was that? What was that? Bloch-Toeplitz matrix. So in a Bloch-Toeplitz matrix, what do you have? Suppose you have 3 by 3 matrices. So each one is 3 by 3. And Bloch-Toeplitz means what? Bloch-Toeplitz means that this block is same as that one, and that one. So you have the same block here. And what about this block? This block is same as that one and that one. What about this block? This block is same as these ones. What about this one? Same. What about this one? Something like this. Be careful. This is Bloch-Toeplitz matrix. And if this is symmetrical, then now we have very similar property with our real valued cyclostationary random process, right? This has symmetry with respect to T1 equals T2 and kind of Bloch-Toeplitz property. But just Bloch-Toeplitz matrix does not have symmetry necessarily, so be careful. Ready? So there is something similar in real valued Y-sense cyclostationary random processes autocorrelation function and a symmetrical Bloch-Toeplitz matrix. Got it? And you will see why this is so. It's kind of obvious. Anyway, so you've seen some important property over real valued second order Y-sense cyclostationary random process with period capital T in the time domain. Got it? And in this paper, we not only utilize this time domain property, but also we utilize the frequency domain property severely to better design, transmit, and receive pulse jointly. Got it? Anyway, sometimes this kind of Toeplitzness can be said as this one by introducing some K, but as you all know from the definition of a periodic signal, the statement, this statement is equivalent to what? this one. So sometimes people just do not unnecessarily introduce this integer parameter k. It just confuses us. Anyway, we are going to say that this t is any real. Got it? In that case, this is a better and succinct, more simple description. Same here. You don't want to introduce some k integer. Got it? So sometimes, even in my paper, I use this integer k, but it's not necessary. So if I rewrite the paper, I would just drop this k here, where it is. Yeah. So sometimes I'm very tempted to rewrite and post kind of revised version of my paper on my web page, but I decided not to do that because no one will read it. Anyway, so here, this definition is applied for complex valued. This is proper complex, right? Complex valued random process. By the way, not yet proper because here just the second order is Y-sense cyclostationary with zero mean, okay? So since zero mean, this mu n of t is 0 for all t in this definition. But you may use some periodic signal as a sample path for general case. But we are not handling that. Got it? And now we assume what? This n of t, capital N of t, is not only second order proper complex, but also it's Y-sense cyclostationary with zero mean. Got it? So we don't need to care about complementary autocorrelation function of n of t in this paper. And you will see in some paper of our paper list, this paper is extended for improper complex cyclostationary interference case. Anyway. And here, the simplest example is the case where additive white Gaussian noise corrupts the output channel. Because Y-sense stationarity means what? Y-sense stationarity means capital T, the cycle period, can be any positive real number. In that case, it's Y-sense stationary. So Y-sense cyclostationarity includes Y-sense stationarity. Got it? A Y-sense stationary random process is a special case of Y-sense cyclostationary random process. What else we need to talk? Let me see. Yeah, as I told you, I was asked by one of the reviewer to not to use star to denote the convolution integral because this superscript and star confuses. But anyway, yeah, this one, as I told you, really I want to put it here now. You do it, got it? Whenever you write a paper, never put conjugation after the parenthesis. You put it in the superscript of the name of the function. Anyway, so yeah, in other parts you may read yourself, but let me see. There is something I need to talk. Okay, so here, positive definiteness of a random process. And this is also very similar to the positive definiteness of a matrix. So let me talk about it. So suppose you have a complex n by n matrix R, which is Hermitian symmetric. So this is the Hermitian transposition. And you should know what's the definition of this one. Okay. So we are assuming the size n matrix R is a Hermitian symmetrical matrix. And here goes the definition. This R is positive definite or positive semi-definite we are going to, if what? In order to define this one, we need to consider Z, that is a complex number, complex vector of length n, and that is non-zero. And if for all Z, for all n by 1 non-zero vector, this Z Hermitian Z is positive. Got it? Then this R Hermitian symmetrical matrix is called positive definite. Got it? And we are extending this definition for a proper complex random process like this. So here first, we consider the autocorrelation function of the random process n. This corresponds to what? This corresponds to the expectation of the outer product of n itself in random vector case. Suppose capital N is a complex valued random vector, and we are talking about this autocorrelation matrix. Then this autocorrelation matrix R is called positive definite if this Z Hermitian RZ is positive for all non-zero x, right? Right? And here, random process is called positive definite if this is positive for all non-zero W. And it's just the kind of extension. See that? We may say that given a random vector Z, right? So similarly, for random process, complex random process, we consider autocorrelation function. And this is positive definite if is positive for all W T non-zero. Got it? So we have exact extension of above notion of positive definiteness of a random vector to the positive definiteness of a complex random process. Got it? And semi-definiteness means what? Anybody? We don't need this one for semi-definiteness. And here we need equal for semi-definiteness. Got it? And if a random process is positive definite is positive semi-definite. Similarly, a complex random process is positive semi-definite, then it's positive definite, then it's positive semi-definite. Okay. So I've talked about the important definitions already. Just a second. Yep. And here goes the performance metric I mentioned last time. So in the figure 1, this one is going to be used as the estimate of BL. So actually, we may call Z of L is B hat of L. And we want to minimize the mean squared error between our data symbol B and the output. And here, since we use the K as the index, here goes the index K. And mean squared error in the symbol estimation is a good performance metric, which, however, requires a lot of caution. Because when you talk about mean squared error between the original random variable and its estimate, we are just using this single performance metric without talking about the expectation of this one and relation with that one. Sometimes your mean squared error minimizing estimate may have different mean with your original symbol. Such a phenomenon is called bias in estimation. So expected value of an estimate of a parameter is not the same as the expectation of the original. So be careful, okay? You must be careful whenever you use mean squared error performance metric. However, some cases, the bias is not that important. Some cases. So this paper, even though I'm just talking about the mean squared error between the symbol and the estimate as the performance metric and develops the results, you may need further constraint in optimization. Here I formulate the problem as actually unconstrained optimization, except the transmit power of the transmit signal. However, you may need one more constraint in some applications. You want to restrict the unbiased estimation. Got it? So be careful. Anyway, here, this R means real part. So you develop the second line from the first line and check whether you have this real part of the product properly appearing in your derivation. Got it? Be careful. Anyway, so here goes the problem formulated as a constraint optimization, constraint only on the transmit power. So this is what? This is transmit power. So transmit signal energy over period capital T that is limited as A. Okay. We may use capital P, but probably if I write it again, I will replace this A with P, but anyway, I didn't do that at that time. So we want to find the pair of waveforms, transmit and receive waveforms, S of t and W of t. That minimizes the mean squared error, subject to, under the constraint that the transmit signal power is A. So problem is very simple. And the solution is not simple. Sometimes very simple problem does not have simple solution. Last time, I introduced the definition of vectorized Fourier transform, and you may not be familiar with it yet. But let me talk more about that one today. And you may have some idea why that is important. So let's see this one first. So if you expand your performance metric, you have many, many terms. Here, 4 terms in your objective function. But if you restrict the power of your symbol as, for example, 1, this is constant, right? And what would be noise power? Is it dependent on our choice of transmit receive waveform or not? Actually, it is. Because this n of k is, as you see here, is n of t times w of t minus lt conjugate. So if w increases without changing its shape, if you scale it, then it increases. So be careful. Ready? Because this is a filtered version, filtered and sampled version of our cyclostationary interference. Be careful. And now, as you see here, this last term, by the way, you may say that, hey, it has k here and it does not have k. And you can easily show that this n of L has same second order, the variance for all n. Why? Because n is assumed second order Weissen's cyclostationary with cycle period capital T. You can show that. Ready? So as you see here, the last term in this 4-term expression is what? Is a double integration of integrand given by the product between the autocorrelation function and received waveforms. It looks very similar to what? W Hermitian RW in your matrix vector multiplication. It's very similar to something like this, right? However, you have double integration. So this problem apparently looks very, very complicated. Not only this last term, all the other terms include integration and something. And whenever you want to optimize some continuous parameter function, that may be called as a variational problem. So there is called calculus of variations. And this calculus is for a function. So function optimization. Your calculus was for what? Just a simple optimization, something like this. See that? Here, this is what you want to find. This is what you want to optimize. And this is a vector. And your multivariable calculus was to solve this kind of problem. But now, what? You have some problem like this. See that? You see the difference? You do not just want to optimize your finite length vector. You want to optimize a function. And this kind of problem is called variational problem. And one of the most famous and seminal problem is like this. Suppose you have a single point here and there on the horizontal line. And now you have a height h and length L. What you want to do is that under the gravitational force with acceleration constant, you want to design a slope without friction, connecting these 2 points continuously. And you want to make some object that just slides, not roll. It does not roll. Arrive this final point E, end point, with shortest time period. And this is given by one of the Bernoullis and sent to also to Isaac Newton. And the legend says that Newton solved this problem after a single night, inventing this calculus of variation. And if you ask high schoolers who are just exposed to geometry, they may say that, hey, the shortest path, the slope that gives the minimum elapsed time would be triangle. Actually, it's not. And you can show that it's a cycloid. And sometimes, depending on the ratio between R and E, sometimes this slope goes even down and up. Probably you've seen only those cycloid slope that connects this S and E above this line, but actually it is not. This is not well known even to the people who know the solution already. I also, when I first heard about this problem, I always thought that the slope is above this 2 sides, but sometimes it even goes down and up. Anyway, so this is a kind of, you are finding what? A function f of x, right? So you want to find elapsed time, and you want to find f of x, subject to f of 0 is h, f of e equals L, it's 0, if of, L, yeah. And they are probably smooth enough so that the point object with some mass can slide. So you may say that f is continuously differentiable. Something like that. Got it? Because you want to use calculus, which means that at least you want to use first order derivative of the function. So probably this is your constraint. Anyway, so if you have this knowledge and viewing this problem, it looks like a variational problem. And let me tell you, only control majored graduate students in electrical engineering are taught about calculus of variations in electrical engineering when they take optimal control. No communications major student, no, of course, semiconductor major students, only control engineering students, because this is also a control problem, designing something like this. Consider you have a drone that requires to determine the optimal path to the destination from the source, the starting point, conveying some Amazon's product. Got it? However, there is a wind. you have limited battery, and the wind speed is different depending on the altitude. Now, what would be the optimal path? That is a three-dimensional line to go to the destination and come back. There could be many paths, or sometimes none. First, you have to find out one solution. Second, probably you want to minimize the spent energy, or you want to restrict the time spent only, right? If it has a lot of power and there is a very large wind, probably it wants to soar up as high as possible. And when the wind is stopped, then it should drop and suddenly break. Anyway, so it's a control problem. And this control problem requires to find a function, right? X of t, comma, y of t, comma, z of t. Vector valued function of t they want to design, right? So control guys are taught about calculus of variations, even when I was an undergraduate student and graduate student. And unfortunately, or fortunately, this era of digital computer significantly changed the approach to variational problems. Now, we have computer that can perform many computations within a fraction of time. So what people do is that even they do not solve partial differential equations. Then what do? They divide the area. For example, usually mechanical engineering guys solved partial differential equation for heat transfer problem. Now what they do is that they divide each material into small cubes and approximate. And then what? You have finite number of cubes, and it becomes a very large, probably matrix or tensor, but it can be computable with high enough accuracy. And that is called finite element method. And this prevails not only in mechanical engineering, but also in electrical engineering when your friends in, for example, computational electromagnetics, for example, RF engineering or antenna engineering, they use this finite element method based solver, partial differential equation solver. Why? Because the Maxwell's equation is basically partial differential equation, right? And also, you may solve some Schrödinger equation related problem using finite element method. You have very small substrate on which quantum phenomenon is evident. Now you want to design some shape that minimize the heat generation for your high speed, high bandwidth memory. Then you need some computation. You need to solve something, but you don't solve partial differential equation directly. You approximate by dividing the entire section into small, very small section, and you use what? Finite element method. Anyway, so this problem, again, can be solved using this approach. For example, suppose this is candidate transmit waveform. Then what do? We may sample it very finely. And assuming that, hey, this is time limited enough for convenience, 0 to some, let me see, 100 t. Then each t is divided by 100 pieces. Then you have just 10,000 by 1 vector that piecewise linearly approximating your S of t, right? So actually, you can solve this problem, the variational problem, without head aching yourself, approximately. Got it? In this paper, we are not doing that. We are solving this variational problem very, very cleverly. That's the difference. We derive the analytically optimal solution, not numerical approximate solution. Got it? So be careful. Even though this paper boastfully derives the optimal solution analytically, you still have alternative choice. This is the difference between academia and real-world engineering. Sometimes you need bypass. Yesterday, my two kids and I visited the Lighthouse Museum in Homigo. And in the second building, there was 3 game boat. So you have some corridor in a harbor, in your imaginary game harbor, and you or my kid should drive the boat. The problem was that there was no accelerator or something. If it turns on, it rushes with the highest speed. The problem was that the corridor was winding a lot, and they had no idea. So they suddenly get out of the lane. So there was limited time before you end up at the destination. And they failed and failed again. And suddenly, I noticed that only the time remained becomes the score. So I found that, hey, why we keep on this corridor? Just to try to find the location of destination and just bypass everything. And my son said, can we do that? So I said, let's do it. And we have score 46, which means that 46 seconds left before we couldn't arrive at all. So what I'm saying is that sometimes you shouldn't be on the track. Okay? You get out of the, for example, box. Sometimes your computer may give you what should be your solution. And that is sometimes very important because sometimes even we do not know analytical solution and what would be the shape of it. But for a specific case, this numerical approach may give you a hint. Sometimes hint of the analytically optimal solution. Of course, not here. Not here. But anyway, so never forget this. You shouldn't be too theoretical in solving a practical problem. And my youngest uncle, who studied civil engineering in his high school, and he didn't go to the college, but he was a very, very fine engineer. And when he joined the company, there were 3 persons, and he was only the high school graduates and 2 of college graduates. And they both tested these 3 people, giving a map of some area, saying that, hey, so this block, oddly shaped block, is our customer's land. And what is the area? And the 2 college graduates tried to approximate, introduce some coordinate, x and y, and approximate the curve with some well-known elementary function, and use the integral to calculate the area. And what my youngest uncle did was that he divided it into triangles. And probably you've heard or you learned in your high school math that given lengths of three sides of triangle, you can calculate the area of it. So amazingly, his calculation was more accurate because usually the lengths are not too oddly shaped. It consists of straight lines somehow, right? It's not consisting of curves. So anyway, so remember this. Okay, we have around 1.5 minutes. So, okay, let me stop here. And just after browsing what is expecting. So what we are going to do is that we term by term convert each term of the objective function by using the vectorized Fourier transform. For example, here, this term can be written what way? Oh, by the way, this one can be written this way. Here, we have a finite integral. And this looks like what? Quadratic form with the W, and this is the symmetrical matrix. Got it? So we are going to convert all the terms of the objective function using our vectorized Fourier transform. Got it? So on Wednesday, you need to read up to section 3, right? So up to here. Ready? And come. Okay, that's all for today.